The topic that we have today is one of the key topics in machine learning, and probably it's one of the deepest topic in machine learning, and there's a lot of research that is happening in this domain. So I thought that I'll get all of you started in this on this topic. This topic is going to be a bit of introduction and a bit of deep dive. So fasten your seatbelts, and I hope this is useful to all of you. Okay, feel free to introduce yourself over the comment section. I may not be able to see it on the, right now. I may not be able to read every comment right now, but I would love to read it later on when I'm after I'm done with the webinar. Wonderful, wonderful. So amazed to see so many people, so many wonderful people from all across the globe coming for this live webinar. And let me just check how many people are there. Wonderful, wonderful. I'm super stoked to see such a great audience as of today. Wonderful. And keep the session live by putting your question in the comments on YouTube Live, and feel free to introduce yourself. Perfect, perfect. All right. I'm going to touch upon the entire reinforcement learning bit by bit. This chapter alone, this particular reinforcement learning, is essentially a 6 months course if you deep dive into it. If you look at the books that I'm going to talk about, they are like 600 pages book. But I'll try my best to keep it super simple and will avoid scaring all of you. Okay, so my agenda will be that all of you are super comfortable with the idea of reinforcement learning and also get a hang of core algorithms of reinforcement learning. Perfect, perfect. All right. So it's going to be a 2-hour session, a brief about CloudxLab. So the CloudxLab started with a single vision, and that vision was to build careers and improve lives. We have been very successful in that. If you take a look at LinkedIn, search for CloudxLab, you will know that most of the people who have attended our sessions, attended our course, taken our lab, or attended our live classes, you're doing very well in your career. So most of you, the LinkedIn would be the testimony for our hard work. It's my personal passion, and this is something that I always wanted to build, and I'm very happy that we are there already. So one of the key things that we did at CloudxLab was creating this lab environment, because when somebody's teaching you, you are basically memorizing it. But with a lab, when you do hands-on, that's when you learn. So we created a lab, and then we hooked the test case-based content, whereby you get an exercise on the left-hand side. On the right-hand side, you see the lab, and then when you do things and you submit your answer, it checks it and gives you points. Now, this is our secret to the success, because our completion rates are above 90%, while the completion rates of all other people who are either pure content-based or pure instructor-led, their completion rates are in single digits. And that's something that, keeps me awake and happy at night, that how can we improve people's learning? If you are able to memorize something, that's not learning. But if you're able to solve a hard problem, that's a learning. And that's our target. When we even, let's take if you take any course at CloudxLab, the soul of the course is that it is hands-on. whether you're taking Python course, Linux course, Scala course, skill course, or you're taking any course for that matter. So, and we've kept it super, super affordable. And I mean, those who are learning elsewhere, what they usually do is they just take the lab from us. And those who are basically starting from scratch, they just take the premium subscription that we have, whereby they get entire content and the lab. So my request to everybody would be that at least take a lab and get your learning going on right away. Okay, because you cannot learn until you really do hands-on. The one thing that I observed at Amazon when I was working with Amazon was that they were able to ramp up fresh engineers quickly because they had the cloud available to the people, and they would give it a boot camp, and you get to tinker around right away. The secret to my learning in general in computer science is that I love to tinker around, do the hands-on, and that's what has made me do good in tech. Okay, so my suggestion is, no matter what you're learning, do the hands-on. You cannot learn tennis, you cannot learn swimming without actually swimming or playing tennis, no matter how much theory I teach you. Okay, so this is the only theory I want to teach, right? That there is no theory, there's no learning without doing. Okay, so focus a lot in your career to do the hands-on. Anything that motivates you to do hands-on, that's the thing that you should focus on. Okay, if I'm telling you, I can tell you all about Python. I can tell you the history of Python, who created it, history of programming language, and I can make you memorize the whole library of Python, but that's just useless. It won't help you. Okay, so you have to be careful and cautious when you're learning technology, that whatever you learn, you have to do hands-on. Okay, that's my personal message, and it's a strong message because, right, whether it's my cousins or nephews or my own family member, this is what I recommend to them. And yes, I mean it when I say that. Whether it's my own child, my nephew, my cousin, even my wife, I honestly, recommend them doing it hands-on way. Okay, so everything that we designed at CloudxLab is for, first is our own consumption, and that's where we got the feedback. So I can guarantee you that this would be the least cost, I mean, most cost-effective way of learning anything. Just take a premium subscription, you get all the things, and then you can plan your career, and you get the entire bunch of things that you can study. So if you're planning to build your career, I would strongly recommend that. Go for a lab-based environment. Don't go for video-only classes, MCQ-only classes. No, those don't help. Those don't help. I've met lots of engineers, interviewed many engineers. They know everything about they know how to talk about something. But the moment I ask a question, they are not able to solve it. So that's one of the reasons why you should always take a hands-on approach. Hands-on approach. You should start tinkering. You should, instead of waiting for what will be 1 + 1, you just go in the lab and start typing that and see what happens. Okay, and this lab is again, I want to tell you very closely that lab has everything that you need for machine learning, DevOps, data engineering. When I say data engineering, it means Hadoop, Spark, and everything. Okay, you get an experience as if you have joined a company and they have given you a working environment and you are working on that like a production environment. You get a seamless experience where you don't need to install anything. There are centralized data sets which you can just use without having to import, export, download, upload. And then you can use all kinds of devices and from anywhere in the world, right? On top of it, as an additional advantage, right, when you are working in the lab, what you have is you have a very vibrant community. So feel free to reach out to anybody at CloudxLab. You can just message them, and in the meantime, it'll build your profile. Okay. At the same time, we have lots of people keep on posting job. If you have a job opening and you want to post it, just reach out to us. We'll post it here. As well as if you are applying, just apply to any of them. Okay. So periodically we conduct these something called placement eligibility test, and the test there's a most recent test that is coming up. Please take a look at that so you can sign up there. Okay. So what we usually do is we conduct a test. Those people who performed well, we connect them to the companies, and that's what we do. And then we have these wonderful courses by IITs, Intel, and our own that you can take up. These are long duration courses. And the first one is instructor-led, and second one is a certificate course. It's an online course. Okay. So, but everything has the gamification and gamified learning library, learning model. And there are courses on almost every new tech that gets you the career, not the tech that doesn't give you a career. We do not want to focus on the courses or other things which are not helping people in getting a job. And you must try these courses. And these are AI, machine learning, data engineering, and others. Okay. All right. That's pretty much. Okay. A brief about myself, those who are wondering, who am I? So let me go back a long back and then talk about who exactly am I. So I did my graduation from Roorkee, and I joined a company called DE Shaw. DE Shaw was a wonderful place where you had lots of data. We had around, we were doing distributed large scale computing, along with we were doing machine learning at some of the data at that point of time in 2002, when nobody had that kind of scale. So afterwards, I started a company. Most of the power plants in India are built using my software. And then I worked with InMobi, then Amazon as the technology leader. And then I founded No Big Data, and afterwards we started the lab, and that became CloudxLab. Okay, so the lab is lab on the cloud. That's why we call it CloudxLab. Okay, so that's about me. I'm very passionate about machine learning. I'm very passionate about computer science in general, and I'm very passionate about teaching and helping people learn. So this is an intersection of all my skills, and that's why this the CloudxLab is something that I really I'm really passionate about. All right, so let's get started. I think that's a good enough intro. Perfect. And all right, so I can see a great number of people joining. Perfect. All right, so one of the things that I want to talk about in reinforcement learning is, what exactly is reinforcement learning? I'm assuming that most of you are aware of machine learning, right? Machine learning is essentially learning from the data rather than manually coding the rules. Like manually coding rules, what does it mean? Writing code in the sense, if this is this, then do this. If this is this, then do this. As opposed to that, in machine learning, we just show the examples of past experience to machine and then let it learn from it. So that's machine learning. Now, what exactly is reinforcement learning then? Reinforcement learning is a part of machine learning. Reinforcement learning is a special case of machine learning, meaning learning, making the computer learn from the experience right? So reinforcement learning is a special case of machine learning. In this case, you have the full environment where you interact with the environment, and occasionally you get rewards. And the most important part here is occasionally. Okay. Occasionally you get rewards. Like in normal life, you don't get rewards all the time, right? You get rewards only sometime, right? And basically working for rewards is in the normal machine learning, for everything you have a reward. Okay. This is a apple. This is it. So you have a label against everything. Every experience has a label. But in case of reinforcement learning, it's that kind of machine learning where reward comes after like 10 steps. Like when you play chess and you win, that's like half an hour later. You have like lots of steps to go till you get a reward. So the core difference between usual supervised learning and reinforcement learning is you get reward after a lot of time, or the label or so-called label or caption that you have to meet, the thing you have to predict, that's kind of in future. It has got to be like multiple steps. All right. That was a very boring way of explaining what's reinforcement learning. A better way is I'm going to show you Mario example. Have you played Mario? How many of you have played Mario? Okay. Okay. I'm sure most of you have played Mario. Okay. And did you learn it by yourself, right? Do you think the computer can learn to play Mario the way you also learn to play Mario, right? Now, so someone actually automated it. Okay. So what he did was basically loaded the game into an emulator. If you want to play that game even now, you can actually load it in emulator software. There are SNES simulators where you can load the game and then play it. So what he did was he basically loaded it into the emulator, and then the software or the bot or script or whatever you call it, it was basically pressing the keys and sending it to the simulator and observing the screen, what's going on the screen. And it learns to figure out how to maximize the score. And that's what I'm going to show you. Okay, so all right. What you see on the screen is it's a day 0, and it just jumping randomly and it dies off an old age. It doesn't really succeed. After a few more few more experiences, actually moving forward, and for no reason it's facing backwards, but it's actually doing something, right? And you can see that it's kind of stuck, it's not going anywhere, right? Now, few more weeks of learning, and now it's there. So you can see now it's playing like me. It has got an intuition. You can see that it has got an intuition, and it is not having difficulty at all. Do you think he'll cross it? Oh, he's waiting for that. Okay. Okay. Do you think he'll cross it? Yes. Okay. Perfect. Now what you see is that he's just playing like a pro. He's just having no difficulties. Now, few more weeks of playing and the computer is really good. You're going to see some magic. Okay. You're going to see computer exploiting the bug. What was that? What was that? Let me replay. See, the Goomba is falling and starts moving downward. So it has figured out a bug in the game. And that's something amazing. So the computer has got an intuition. Computer is just trying to figure out how to, win it. Now, the another bug you'll see how to exploit is this. What was that? I have no idea. So this is after a while, it was able to play most of the games except for this. When it could not win the game, it kept on pausing the game. Okay, it's as if your greedy cousins, when they are not able to win against you, they just spoil the chessboard and run away. Similarly, it just kept on pausing the game when it could not win, because if it pauses, it would not lose. So what you see is that this is intelligence. This is intelligence. And I mean, one of the very important thing that I wanted to convey with this, that computer or the machine learning model that's playing this game and learning to play this game is essentially doing the reinforcement learning. There's an environment, it moves certain steps, and in the future, he gets rewards, maybe after 4 steps or 10 steps or 20 steps. Okay. And that's the most important part. So you have the environment, you have a player, and the player or the agent moves in the environment. The machine learning model predicts what action to take. And that's what is reinforcement learning. The difference between reinforcement learning and this is that you have, one of the core ideas of reinforcement learning is that there is a environment that you get to play in. All right. So this is a general diagram that we have. So there is an environment, there is an agent. Agent takes some action in this environment. The agent may or may not get a reward, and then the environment changes, and then agent again observes the environment and then takes another action. And that way, the agent keeps on doing over and over. Now, this might look complex when I'm explaining, but if you think about yourself, what is it that you're doing? You are doing reinforcement learning. The world around you is your environment. You are taking an action. You may or may not get rewards, but because of your action, the environment changes. Like I pick a glass, for example, and the environment changes. And when I drink it, I get a reward that I got water. So this reinforcement learning is actually life, right? So that's what we do. We are so good at it. We are so good at it that nobody even has to teach us. There is no reward. Like in childhood, we did not have a reward, right? Nobody told us in childhood that, oh, if you play with toys, you will get rewards in future. No, we learned everything by ourselves. By the way of this machine learning model that we have, we basically explored things. We learned about the behavior of things by ourselves. And that's the upper level of reinforcement learning. That's where we, like the whole computer science industry, the whole machine learning industry, that's where they want to reach. That can we build a machine, or can we do a reinforcement learning to such an extent that it can roam around the environment and figure out its own rewards and live and build things and live happily. So that's reinforcement learning. Now, you might think at this point that reinforcement learning is only this environment. What I'm going to show you is that reinforcement learning is used at many places. Okay. All right. So what the goal of an agent is to maximize the reward. Okay. Now, since reward is sparse, okay, you did 10 things and then you got rewards, right? Because of these 10 actions, right, you got reward, but you can't really credit all the 10 actions, and you can't even credit only one action. So you got to figure out how do we credit the actions that we have taken, okay? And that's essentially one of the hardest things, okay? Like even in case of you, when you're training an animal, when you are training an animal, for example, right? If you give it reward after, say, 2 days, okay? Your dog played with you today, but you gave it reward after 2 days. Will it learn? No, right? And that's very true with most of the machines, okay? The longer chain of actions you have, the harder it becomes to learn, okay? I'm going to talk about that soon, all right? So the agent acts in the environment and learns by trial and error to maximize the reward. Now, question is how to apply these rewards in real life. Okay, so I'm going to just briefly give you an overview of a couple of examples. Imagine that you have to build a walking robot, right? So the agent is going to be the program that controls the walking robot, or we call that policy. And there is a real world, which is environment, like the physical world where this robot is going to walk. That's the environment. And then this agent is going to observe the environment through a set of sensors, such as cameras and touch and infrared sensors and so on, or LiDAR, for example. And then it's going to take actions. It's going to, what kind of action can a robot take? Send signals to activate motor, right? Whether it's about moving a leg or turning around, it's all about activating the motor. And those are the actions it's going to take. All right. So when you are coding this kind of thing, right? Now, question is, what should be our reward, right? So we could give rewards to it when it approaches the target destination, and negative rewards when it wastes a lot of time. The question is, which action should agent take to maximize reward? That's the thing that machine learning model need to figure out. This approach is called policy search. Okay, those who are still wondering that is this of any use? Yes, you'll be amazed to know that things like ChatGPT, they were built using reinforcement learning agents. So there are two brains, one that is predicting the next word, and then there is a reinforcement learning object, reinforcement learning model, for which the world around it is essentially the words produced by the big agent. So there are two contenders, and they're working together to give you the best answer. So, and you'll find it very common in most of the reinforcement learning is that you have two brains, right? The way human has left brain, right brain, you'll find it in many of the reinforcement learning approaches that there are two brains. One doing the prediction, other criticizing it and trying to figure out whether that action is good or bad. So if you take a look at multiple algorithms in this domain, you'll find that. Now, other than robotics, there are so many use cases of reinforcement learning, whether building the persona of your customer. Let's say you are Facebook and you want to understand what will this user do, or what should we show to this user so that the user remains engaged. So for that agent, the user is the environment, because the agent presents something to the user, meaning takes some action, and the user gives a feedback. Okay, if the user likes it, That means you got a reward. If the user did not like it, you got a punishment. So reinforcement learning agent, in case of say Facebook, like you have to optimize news feed and you are trying to figure out how do I produce, which video should we show to this user so that the user is engaged and happy. So you get this, you build this agent which is trying to figure out the behavior of the user, and that behavior of user is its environment. So that is one. Second is, imagine that you are working on coming up with lead quality score, right? You are working in CRM, like if you must have used customer relationship manager tools, you will have something called lead score, right? Lead score is a classic example where you can utilize reinforcement learning. Similarly, there are many use cases, like for example, auto trader. The market is the environment for auto trader. The auto trader takes an action, market gives a feedback, and then it keeps doing that. So there are so many use cases of reinforcement learning. And when you basically have any like continuous environment where you get the feedback continuously and so on, or you get a sparse rewards, like after doing 10 actions you get something in return, or after doing say 500 actions you get something in return. Now those are the use cases of reinforcement learning, whether it's medical science, anything. You will see that reinforcement learning is going to be there, because in the real world the concrete rewards do not exist. Most of the machine learning where you have a supervised learning, this is Apple, this is it, this is it, right? There, somebody has to label, right, that this photo is Apple, this photo is that. Somebody has to label it. Therefore, that doesn't work. Okay. In most of the cases, the rewards are very sparse. The labels are very sparse. And in those cases, you utilize reinforcement learning to a large extent. Okay. Now, all right. So coming up with a policy or a strategy is called policy search. Policy is essentially the algorithm or the model used by the agent to figure out what actions to take. And policy search helps figuring out that policy, right? Policy search is essentially, when we say that, okay, I'm thinking, what does it mean? I'm thinking of the strategies, right? So policy search essentially is figuring out what policy is great. Now, so it's as simple as this. The agent has a brain called policy. The agent is going to take action based on the observations and the rewards it got in past. And it learns this during the training phase, and it uses it during inference phase. All right. Similarly, if you think about a robotic vacuum cleaner, and your reward is how much dust it picks up in 30 minutes. Its policy could be figure out chance of moving and chance of turning. Should I turn or should I move? Right? So you have to figure out two variables. What is the chance, or what's the probability, or what's the intention to move? Like how much is the bias for action, and how much is the bias for pivot? So these two variables you have to figure out in this case of policy at P and R, right? These are the two variables. Now, if you're going to figure out these two parameters, the probability of moving ahead, and other is at what action should it turn, right? Now, you have to come up with all possible values for P and R. P is for how much fast it moves, and R is how much it turns around. Okay, so there's a huge, space that to search. If you are going to be, let's say here, like it's lazy in turning as well as lazy in moving. This one turns a lot and also moves faster. So you can see if let's say you're here, whereby it turns a lot, it rotates a lot and moves less. So it'll be basically just doing this, just sweeping the room only in one corner, right? But if you are D, like you move forward fast, right? Then your trajectory is going to be like this and so on. So finding that optimal parameter of P and R such that it sweeps the whole room is going to be your policy search. This is a brute force. One brute force could be that we try all possible permutations of P and R. If there are, let's say, 100 values for P and 100 values for R, we basically try 10,000 gameplays and figure out which of the gameplay is giving us best results. Okay, so essentially that's brute force. Brute force literally means that you are applying force in trying all permutations. The other is a little greedy approach in which what you do is you randomly pick values of P and R. Okay, you create 100 such policy, and then you pick, right? You observe. After a while, you just give them a time of say 10 minutes. After 10 minutes, their life is over, and whoever did great, we just pick those ones and make slight changes to their PNR values, and then again keep on trying again and again. So this way, you kind of go a bit greedy. You just start supporting which did well in the beginning, right? This may not give you the perfect solution, but it'll give you good enough solution, but without trying all possibilities. Okay, so this is called a genetic algorithm approach. This is genetic algorithm, but it is asexual because there is no mixing of the model. It's only one parent, like one parent giving birth to so many children. One parent giving so many birth. What does it mean by giving birth? It's just taking this probability, making tiny changes to it, and so on. And then we basically do that. And we keep on picking it and then again repeating the process. Eventually, what will happen is only those policy will be remaining that essentially are doing best. Okay, because you're killing the laggards very quickly. So you're not wasting too much time or too much of CPU cycle in trying the worst policies. So you have to figure out what's the minimum survival time you need to keep and so on, and how many children do you need to produce here and so on. So this is called the genetic algorithm. Specifically, this is a asexual genetic algorithm. Okay, asexual reproduction, we call it. Okay, because it's a single parent. Perfect. Now, the other more greedy than a greedier approach or more greedy than the genetic is using the optimization technique. What we do is we try to change P a little and observe the impact of P on the outcome. If it's going good, then make P a little bit more. And similarly, you try R, one of the parameters. I'm just taking two examples of P is for your tendency to move forward, and R is the tendency to turn around. You slightly change them and then observe, are you getting better or worse? If you're getting better, then you move, twist it more, otherwise you go back. So that's called gradient. Gradient is rate of change. Okay, so you tweak the parameters by following your reward. How much benefit in rewards are you getting by tweaking one of the parameters? And this is another policy search algorithm. This is called policy gradients. Okay. So most of the neural net-based policies, deep-Q-learn or A3C, most of these algorithms are based on the optimization techniques. They're not based on genetic. They're not based on stochastic. We usually call this one, brute force or stochastic, like probability-wise, you just pick up things. Okay. Now, moving ahead. Okay. So The question is how to make reinforcement learning more efficient. Okay, so yeah, so there are many more techniques to it. One of the techniques is right to so how do we make reinforcement learning work? How do we make it happen? Okay, one of the techniques is using replicated learning. Replicated learning is something interesting. It's like cloning your behavior, right? Um, so a long back in 1950s, one of the professors from MIT was trying to create a autonomous vehicle. What he was doing is he was taking a photo, he was taking a video, which using a desk cam. He just put a camera there, and basically he was at every stage he was recording whether it's the whether the given this photo, should we turn left, should we turn right, should we keep moving, should we accelerate, should we apply brakes, all of the actions he was recording. Okay, meaning that given a situation, this is the action. Okay, so that kind of data he gathered. Okay, of course, it did not perform great, but that experiment set, expectation or set a direction for a lot of reinforcement learning, right? So you have situation and action to take, situation and action to take. The policy or policy search is going to be this: look at the photo and predict the action. And you have the historical actions given for historical photos, and based on that you learn so that given a photo you should be able to tell whether to apply brakes or whether to keep moving. Okay, so essentially this strategy is called replicated learning. This is the easiest form of reinforcement learning. This is the 0th example of reinforcement learning. Okay, it's essentially a supervised learning whereby you have not done anything new. You have the label for every situation. Okay, and you're just training a model to learn to drive car based on that. But even though it might look very rudimentary, that replicated behavior, because we are making the computer clone your behavior, right? Even though this approach looks rudimentary, but it's not uncommon even today. It's not uncommon. It's used a lot. It's used a lot in many circumstances. Okay. Now, this strategy called replicated learning is used a lot even today. Okay. All right. So this is essentially, you have lots of environment. You basically, what you do is replicated learning is essentially behavior replication. Given a human behavior, try to replicate it. Okay, that's about it. And you might ask that what is so good about replicated learning? Isn't it same as supervised? No. In replicated learning, you keep the historical actions as well. So next step, when I'm applying brakes is based on past 10 actions. Okay, not only the current one. Okay, not only the current one. And that's what makes replicated learning also hard. Okay, now, all right, feel free to ask questions. I'm going super fast. I know that it's a big subject, it's a humongous subject, and I shouldn't be rushing into it. And I would strongly recommend, if you really want to go through reinforcement learning in detail, go through my course at CloudxLab. There I have spent around 12 hours, not 12 hours, 16 hours into this 15 hours into reinforcement learning, doing hands-on, going step by step, breaking down everything. And here I'm just rushing into it. I'm just moving fast because I have to answer your questions, as well as I want to give you a holistic picture of things. Okay. Before this, there are lots of things that I'm not talking about, because I feel that those things, you can figure it out by yourself. Okay. And in the interest of time, I honestly want to tell you that it is worth spending time on reinforcement learning. If you are okay with, supervised learning or normal machine learning, it is time to move to reinforcement learning. Okay. And reinforcement learning is not like, okay, I am into computer vision, so I won't learn reinforcement. No. No matter which branch of computing you are with, reinforcement learning is going to be there. It'll improve your approach in computer vision. It will improve your approach in NLP, because if you think about ChatGPT, ChatGPT was about recently done by OpenAI, which is probably the smartest language processing example that you have historically. So if you look at their approaches, like on top of GPT, they created ChatGPT, which can answer any of your questions and can talk to you. So that kind of, if you look at their paper, you'll realize that they used reinforcement learning. So no matter what's your branch of study, branch of research, reinforcement learning will be useful to you. Okay, reinforcement learning will be useful to you. The only condition that is there is that you have to make yourself comfortable with general machine learning, supervised as well as unsupervised, and deep learning. Okay, and you will become, once you are comfortable with the backpropagation, you'll become comfortable with the algorithm that we're talking here. Similarly, there are lots and lots of lots and lots of examples out there that you can try. All right. Okay. So one of the wonderful things that happened was in case of machine reinforcement learning recently means like 2016 or 2015 or 2014, was deep Q learning. Okay. The idea was extremely simple, right? The way we look at something and then say, oh, this is nice, right? So coming up with whether something is nice or not, that's an intelligence. We look at, let's say, I'm starting to play a chessboard, okay? And I'm given this chessboard in the midway, and I look at the chessboard and say, oh, I'm in a nice position, right? So that nice, when we say that emotion called nice, right? That emotion called nice is a Q value, okay? Given the state of environment, coming up with a Q value is saying that nice feeling about that environment essentially is the Q value, okay? And there are multiple ways of judging it, right? Q value is usually, what we do is we take a neural network, make it look at the environment, and ask the neural network that, hey, what do you think? It says, okay, the Q value for taking this action is this much. Q value for taking this action is this much, meaning it'll give us this much benefit and this will give us this much benefit and so on. So predicting those actions and that feel good about predicting those actions is Q value. And And, you know, when we say that, when we look at a place and say, okay, this place is nice, what is it that we're looking at? If you look into your heart and think about it, right? What are we looking at? We are looking at, okay, if let's say there's a design, there's a house, and you look at, okay, and you look at it and say, oh, this is nice. Right now, you will not realize how much calculation you have done. You must have seen, okay, this chair looks very comfortable. It doesn't look like it'll break. It doesn't look like dusty. Therefore, it's not harmful. It doesn't look like it's disaster or dangerous to us. There's no sharp things around it, which might hurt you, right? So all of those calculations you did in a single shot, right? That's the key value. That's the Q value. Okay. Q value is that feel good factor about the environment. Given an environment, tell me whether it's good or bad. Okay. So we want to train a model which can look at an environment and tell us that is it good or not. Okay. So imagine that you're given this chessboard and white to move, and white needs to figure out whether, like, is this state good for me, or is this action good for me, and so on. So that definition of good or bad, how much good is it? That's Q value. Okay. So what we do is we ask neural network that here is the environment, here is my chessboard. Okay, here is your chessboard. Look at this chessboard and tell me what is the Q value for each of these actions, right? Should I move this? Should I move to this side? Should I move to this side? Should I move to this side? And so on. It would tell us all possible actions that we can take. And what's the probability of all of them? Okay. So this is the beauty of Q learning. I mean, deep Q learning. So we train a neural network to predict the emotion or the likelihood of winning when we take an action A. And when we take an action A, the environment changes, meaning the board changes, and we reach to another state called board, and then we do it again. And that's what is that's what is our agenda. That's what we want to do. We want to build this kind of brain which can give us all these probabilities or all these emotions about every action. And whichever value is maximum, we take that action. Okay, if the Q value for action 2, Q value for action this is highest, we move that. Okay, so we basically compute all the possible actions, the Q value for all the possible action, all the pair of state and action, and every time we take an action, we'll get into another state, and then we'll do it again and again. Okay, now question is, how do you train such a model? How do you train such a model? Okay. Okay. So those who are not aware about the backtracking tendency, if you have coded, let's say, tic-tac-toe or something using normal code, what you usually do is that, right? First, here we take one action, any random action. Okay. Then the same code takes action on the behalf of the other and returns whether the other person will win or lose. If the other person will win, then we don't take that action, and we do it recursively. So this strategy in computer science is called backtracking. You make a move. You don't make a move. You basically think of making a move. You think of making a move, and then you think from the other perspective. Same function gets called again from the other person's perspective, and then if it wins, then we basically undo that move and then put it elsewhere. So if the opponent wins, then we think of it as loose to us, and then the same thing keeps on going over and over recursively to thousands of steps. Okay, so in the usual way, when we are doing the, let's say, the normal computer science, not the machine learning, we'll just recursively try all possibilities, right? But here we don't have that. That's not something that works out. We know that because trying all possible things recursively is not really optimum, right? Because um, in a game, even like a chessboard or even like game of Go, basically it's just impossible to try all possibilities. Therefore, a normal computer won't be able to meet that. Or even taking many actions is going to take infinite time to make that move if you're going to try all possibilities and try all possible things, right? And the that's why the AI or the intelligence does a way better job. Now, just like human, we look at the board and we look at, okay, this thing seems good when I move it here, this thing is safe, and I'm in a good position and so on. So we have built an emotion around every action or every board state, right? And that's what we want to build as part of neural network. Question is, how do we train this model? What is our label? Who is going to give it this label called Q value? Are we going to sit down and put down that, okay, if we are in this situation, that means we have got a high Q value. It's nice. And it got 10 score, it got 9 score, it got 9.5, it got 9.02, and so on. Like, how many can we set? We can't, right? We can't really define the Q value like that. Therefore, what we do is, the algorithm is just amazing. You just, pay attention to it. So what we do is, okay, so what we do is we take an action. Okay, we take an action, right? So we were in an stack and we let it play for a while. Okay, so we let it play for a while just like that. Okay, imagine that we were playing this board and it made a move. Okay, so it made one of these things move. Okay, this one made a move. So we have the record that we made this particular move. Did we get a reward? No, because right now we did not win. But so, or maybe we won or we got some reward. So we have a record that when we moved from one state to another by taking this action, we got this much reward or we got no reward. Okay, so we have this historical data. Okay, so what we do is we ask the model we ask our neural network model that here is the initial state, tell me the value of it. It tells her, okay, these are the possible actions and every possible action has got this much of niceness associated to it. So what we do is we basically sum up all that. That summation of all the things represents that summation of all the actions, all the niceness of actions, right, gives us the value for the current board. Okay, so we got the current board's value by summing up all the possible actions value, right? Now we went to the next state. Okay, we went to the next state. In the next state, again, in the next state, what we did was we again evaluated the niceness of it. Okay, using the same model. Okay, so and then we added reward to it. Okay, so now we have got the label, right? If taking this step led to a good state, that means my current state was nice, right? Current action was nice. And that's how we train it. So the same model predicts the next state's values and we add the reward to it. That becomes the label for us. And that's what we keep on doing over and over. So it might look unstable to you because it's the same model which is predicting for the first state and second state. And basically that's how we train it. It's essentially like saying this, that okay, keep playing. If you will build emotion about the board based on, you will build emotion about taking an action based on what you learned in the past. So essentially, that's what we are doing here. We basically okay. All right, let me just, yes. Okay, let me just try explaining again, because this is a bit hard, and I'll try again. So how do we say that the board is nice or not? Okay, so we have the Q value for the pair called state and the action. Okay, so the neural network predicts these values. Initially, they are going to be way off. Okay, they're going to be just random numbers initially, right? But as it start getting rewards, it will start tweaking these values, right? It will start trying to predict that, okay, when you are in this state and you make this move, you win. Therefore, this state is nice. And then it comes back and does that recursively. Okay, so essentially, based on the reward it'll get in future, it'll start figuring out and understand the value of each of the board steps. Okay, so neural network predicts, right? Okay. All right. Okay, so let me try to draw it. I think I'll be able to explain it. Okay. So we got this board state. We were here. We took an action A1 and we got here B1, right? So using the neural network, we predicted all the possibilities of all the actions, and we summed it up and we came up with a Q value for this, right? This Q value is predicted. Okay, this Q value is predicted. Cool. So we feed it to the brain, to neural network, it gives us something. Initially, this is going to be mostly like random. Okay, now what we did, we know that we moved from B0 to B1. Again, we asked the same neural network to give a Q value. Okay, let's call it Q final. Okay, and we got Q final, and we also got some sort of reward. We were playing a game, we were at this state of the board, we took some action, we reached here. Okay, and we're looking at after say 20 plays, after we have played like 20 times or 100 times. Okay, and we got some reward here. Okay, so this QP, the QP should be equal to reward plus final Q value. Okay, so we are saying, we are telling the neural network, hey, this value should have been equal to this, right? So learn from this board such that you are predicting QP equivalent to this. Okay, so again, we played some game, we played like some game 10 times. Okay, and we have a record of those gameplays, right? Each action. So our environment was in B0 state. We took some action called A1. We went to the B1 state and we got the reward. So we have a history that B0, A1, and this reward and B1, right? So this is the data we have historically, correct? Now, We pick up this historical data. I'm talking about training a neural network. I'm talking about deep Q learning. We pick up this historical data. We pick up the initial state, feed it to neural network, and it says, okay, I'm predicting this. All right. Now we ask the same neural network to predict the final value. So we get some Q value. Okay. It says that, okay, looking at this board looks like this much nice. Looking at this board, it looks this much nice. Okay. Now we go back. We have now this value of, okay, the value of the B1 is QF and B0 is QP. We say that, okay, now learn from it. Okay. This tweak your knobs such that this value should be equal to this value. Okay. Tweak your knobs. A neural network is nothing but a bunch of knobs, okay, which we apply these bunch of knobs into some input. It gives us some output. So we are saying tweak your knobs such that QP, the result of this one, these two should be equal. And that's about it. Okay, that's about it. So basically, on the prima facie, this is a fairly simple algorithm, but when you go on implementing it, it's going to be a bit harder. All right. Now you might ask that you told me that this neural network predicts the Q values for all actions. Yes, it does. This value that I'm talking about is the value of the board, which is basically summation of all actions. Okay, we call that all actions, right? It'll give all the values. Neural network will give like 1,000 values. We are summing up all of that. That becomes our value of the board. Okay. Like, I mean, in an environment, if you are able to take more actions and more actions look very healthy, that environment look healthy to you, good to you, correct? That's what we are doing. We are summing up all those Q values or feel good factor of all the actions. And that's what is QP. Okay. So QP is that, and QF is the value of the final neural network. Okay. And we basically tweak these knobs until these two values match. Okay. And that's what is about training. All right. And the question is, where do I get these values? Like I said, you basically get the initial and final. Yes. So what we do initially is that we make this agent play this game around 100 times, and it gathers those 100 steps data. And then once we get the 100 steps data, right now this model is just playing randomly. Initially, it'll just be randomly playing the game. Okay. And then we get some data, and then we start training it. And then again, we make it play after it learns a little bit. Again, we make it play. And then again, we retrain it. Again, we make it play and then retrain it. So essentially, it's like, you know, we wake up in the morning, learn all the things in the day, you go to sleep, our learning is happening at that point of time, and then come back again in the morning, and then again start playing. So the same thing, we do it here. Okay. All right. So I know that this is, I'm trying to make it, there are many things that, many details that I'm missing out right now, because this is supposed to be a semester course or maybe a year course. And I'm just trying to cover I've skipped lots and lots of things. Okay. I've tried to make things super simple so that you know what's going on underneath that. Okay. So like, for example, training or backpropagation, the way I explained it is that neural network is a bunch of knobs. When you feed the input to it, it gives some output. And training is nothing but tweaking these knobs such that we get the output as per our expectation. Okay. So, and these knobs, the strategy is that you start tweaking the knobs from right to left, and that's what is called backpropagation. Okay, so I mean, if you guys are interested, just take a look at the CloudxLab's backpropagation from scratch. And those engineers who are planning to get into machine learning or neural network, that blog post I would strongly recommend. Okay, no matter whether you are an engineer or a scientist, go through the backpropagation from scratch by CloudxLab. That's going to be super useful to you. Okay. Okay. All right. So now a little bit of engineering, and I want to give you a brief of idea. Okay. And I want to keep some time, probably I have 10 more minutes left, and I want to keep some time to answer everybody's questions. So a number of, the great things have happened in past in machine learning. One of the greatest things that have happened is this emulation or simulation environment. Somebody who actually the game that I showed you in the beginning, where computer is learning to play Mario. At that point of time, a lot of energy went in just trying to make it emulation work with the software, and the whole engineering took a lot of time. But we're living in a time where all of that has been made simple. And as a matter of fact, most of the machine learning reinforcement learning agents are trained using these simulated environment called gyms. Okay. OpenAI calls it gym, and other people call it a simulator, and so on. Okay. So now, on one hand, these environments became super simple, honestly super simple, and a singular API where you can just talk you can just interact with the environment. You can just, you can say import gene from OpenAI. I mean, you can just do it at CloudxLab, and it's there, right? Import gym. And then you have the gym, and then you say, okay, give me the instance of this particular game, and it creates a game environment for you, and then it gives you the states, and then you interact with it, and you ask it to do a replay, and it shows the image of all of that. So this is an amazing part about today's time, and one of the greatest things are these online simulators. Okay, all of them are like open source, free. You should give a hands-on to it. I mean, try it hands-on. Okay. I mean, in my course, I mean, the entire thing is hands-on, in the sense that we start with a simple pole cart example, and then we learn how to balance using a card, and there's a pole balancing on it, and then we try to move it, and we teach machine to balance it by itself by looking at the past history, and it's so simple. It's so simple. So the other great thing that happened in recently was the TF agents library. So when I was coding my cart, whereby I wanted to build this agent whereby there's hardware and it can roam around my house, learn from the environment, and so on, I had to code up lots and lots of things. I had to code up a agent that is there in the car, and it's recording all the actions and sending it to the server. On server, I had to code it up like there's a deep Q learning agent, which is basically, training the model and then shifting the model to the car. And it was just too painful. It's just too painful to code up everything from the beginning. There were so many edge cases that I missed out. But the beautiful part is you don't have to do all of this now, because you have like TensorFlow agents, entire library, which does exactly that. Okay. So you have all kinds of probably like 400, 500 games in this OpenAI gym, board games, Atari games, simulations, and so on. Okay. And one of the things you should try it out is this pole cart example. Okay. So Like for example, this one, right? All right. So here, right? Just take a look at the, if you say go to import, I mean, you just clone this repository to your CloudxLab environment. Okay. There you'll find this, you basically run this setup. That's a normal one. And of course, this is borrowed from other researchers who are working out there, and a little bit modification. Specifically, I personally like the book by Aurelian Geron. Okay. And if you are really inclined to give it a shot, you must try this book. Okay. I mean, the newest version of it. Okay. Newest version of it. I think this one is not second edition, third edition. There's a third edition out there. Okay. There is a third edition. I don't know where is the third edition. Okay, so those who are planning to start, probably this would be no. Okay, which okay, there's a recent edition, like 2022, like a new one. This one is old one. All right, just take a look at that one. So we usually follow that book. Also, there's this amazing book about reinforcement learning by Sutan, and it's actually open source. If you want, you can just go to this website and go page by page. But the problem with this book is that it's around 600 pages. Okay, and you wouldn't really like to spend too much time. I would say that a shorter course, a shorter chapter like by Aurelian's book or my course, if you go to CloudxLab, you can find that course. And there you can just start doing that. Now, coming back to it, so if you just do at CloudxLab, you say import gym, and you can just take a look at all the games. You'll see that there are thousands of games that are there, right? You can just create environment for anything. Like you can just, like for example, card pooling game, you can just say gym.make and it'll give you the environment. And then the moment you say environment or reset, that means that we want to start the game. It returns you the observations. Here in this case, there are 4 observations: the angle at which the pole is there, the velocity of the cart, and the angular velocity of the pole, and so on. So you get these 4 values in return. Okay, so you're playing the game in numbers. Okay, and you can actually just get used to this, like in case of metrics, the way they get used to looking at the metrics screensaver when numbers are falling. So in the same way, you should get used to looking at the numbers. Okay, so here you can just say that environment dot step, meaning take either move left, move right. Okay, and again, the moment you move left or move right, it returns you observation, reward, whether the game is finished, and other information. Okay, so essentially, this is the single common API or common functionality almost every game in OpenAI Gym provides. The only difference is what action do you take and what is the dimension of observation and those and the info. So essentially this is a common API whereby you say environment.reset, or you say game.create, and so on, game.make, and so on. Now moving ahead, so here that's what it is, and you can just start with a very simple policy. Like policy here, the policy is so simple that if the angle OBS2, the third observation, if the angle of the pole is less than 0, which is tilted to left, turn left. If it is greater than 0, that means it's to turn to right, turn right. As simple as that. So this is my simple policy, and what I can do is I can play this game over and over. So this is not a machine learning, it's a rule-based system. And we can use this strategy. We can use this strategy to train our machine to learn from it. Okay. So right now it's just not really machine learning. It's just a simple rule-based approach. Okay. Then you can take a look at this notebook and make sure you're comfortable with it. So here we are creating a neural network model. Okay. And this function, what it does is it takes the model and runs it and renders the results. It returns how many steps we have taken in different environment right? So essentially, here is the code that essentially gives you a fair bit of idea about reinforcement learning, though this is just replicated learning and is standard supervised learning. It's not really reinforcement learning, but it'll give you a fair bit of idea. So what we are doing is we are here, the label expectation from the model is that in case the angle of the pole is left, it should predict the turn left, move left. If the pole is right, move right. That's what we are saying here. That's what we are saying here. We are, hard coding the expected action. And we are saying that we know best, and this is the only approach, and learn from it. And the machine is learning from this approach. Okay, here, this is replicated learning. Why? Because we are asking the model to replicate our behavior. We are saying that this is the best we know, that in case the pole is turned to left, turn left, otherwise turn right. But this may not be the best solution because there's an angular velocity of the pole, at what rate it's falling, and so on and so forth. Therefore, it may be that it's on this angle, but it's moving to the right on certain angular velocity, and therefore uh, our approach could be wrong. Therefore, this approach is just very rudimentary and basic. Okay. But this gives you a fair bit of idea. And that's when we go for, say, other strategies in this game, whereby we do not judge it now, we let it play. And then using the Q-learning and others, we basically predict the next one. Okay, so I leave that to all of you to, give it a shot. Okay. And you could just go to, say, here, CloudxLab, deep learning specialization TF2, and then, there you'll find a folder called reinforcement learning. All right. So, and you can just take up a CloudxLab account and start tinkering around it, and that should be good enough for you. Okay. So, like, for example, for me, I've just cloned it in my environment. Okay, I'll just go to another account, my personal account. Okay, so there you can, right? So usually that's how we, like, all the learners and everybody, including myself, all the people, my team and everybody, just uses the lab and gets things done. Otherwise, it takes like months to set up your environment and it never happens. Okay. So this is my lab, and in the lab, there are credentials, and I can start just here. So this is lab, and then you can have, the entire my courses and everything. Okay, so here is like a full Jupyter notebook and so on. So here I have cloned these notebooks. I'll just pick this particular repository. I've cloned it from GitHub only. This is also available there. And you can just take a look at this reinforcement learning and here, and I can start running it. Okay. All right, looks like my computer is like superheated. All right, I think my computer is superheated. All right. So you can see, I can just, run everything here simply. And like it's initializing gym, loading the gym, importing the gym, and then I can take a look at that. Okay. So you can start tinkering around it. All right. Cool. Okay, it is initializing. All right. My computer is like superheated because of Zoom and all. Okay, so you can give it a try. All right. Perfect. Perfect. So yeah, that was a brief hands-on. So give it a try, take a look at the notebook and start tinkering around. That would be my strong personal recommendation. Okay. You can just take a lab for a month or so, or if you want, you can just take a premium subscription. And it's not costly. We are keeping it very, very low cost because we have to pay to Google and Amazon for these services. And not only that, in lab, you get like Hadoop, Spark, and entire paraphernalia, along with like data sets and everything. So I think the membership or subscription fees for the lab or the premium courses is extremely reasonable. Okay. Now, there are many variants of deep Q learning, and those things are something that you should pay attention to. So there is double DQN. Okay, so basically DQN, two models competing against each other. That's a double DQN. And I'm not going to go into too deep into this. And yeah, so I'll just move ahead. Then there is a dwelling DQN. Take a look at that one. And yeah, moving ahead. Yeah, one more thing that we missed out here. I strongly want you guys to take a look at a couple of more things. If you are really interested in this. Okay, so there's this amazing paper by Deepak Parekh, and it's basically he designed something called curiosity. Curiosity, like how can a reinforcement learning agent learn by the way of curiosity? And the results are just amazing. Results are just amazing. You should take a look at this. And what happens is that not this one, not this one. Okay. Yeah. Take a look at this one. Okay. If you are really, really, interested about how do we think, this is probably one of the things you will be amazed. And you'll get lots and lots of answers to questions like what is entertainment and why, what is that? So in this video, what they're showing is that the agent which was trained using curiosity when there was no reward given to them, okay, given to the agent, it was able to play almost all the games without any explicit reward. Okay, it figured out everything by itself, just like humans figure out everything by themselves. Okay, now one of the things that it further shows is this. So what it does is basically the model even learns to navigate really complex paths without any rewards. There are no rewards, and just out of curiosity, it does. It avoids boredom, and how it defines boredom is very interesting. How does it define curiosity? It's just amazing. So it's my personal favorite. You should take a look at. the curiosity learning. Now, this is amazing. One of the amazing thing was that when they put a television in this, just because agent was learning by curiosity, it was trying to maximize the information gain at every point of time, right? The moment the moment a television was kept in this arena, it started becoming couch potato. It did not move. It just kept on watching television. Okay. Yeah. So that was something there. I'm not able to figure out where they have mentioned it. You should take a look at that paper, and probably they will have more videos out here. Okay. So this is one thing I want you to take a look. Curiosity-based learning. That's a paper. The next thing I want you to take a look is thing called one amazing part was A3C. Okay. A3C is actor. Okay, so I think A3C is, I've not mentioned it. It's basically called asynchronous advantage actor critic. So you have two models, one is critic, another is this. So take a look at that. That's something that is very, very often used. Okay. So probably this would be a good idea. All right. So just take a look at that once you are through with the reinforcement learning. And okay. Yeah. So I've already talked about this part that Google DeepMind basically trains a lot of right. So in case of ChatGPT, they took GPT model, used a reinforcement learning agent, and trained it to give better answers. Okay. And a lot of self-driving cars and everything, they use reinforcement learning to a very large extent. Okay. Now, yeah. So there are a couple of challenges. I'll just skip this part. Probably you will, right? So there are challenges with respect to reinforcement learning from the technology as well as data perspective. And there's always these models are fairly unstable because sometimes they just keep on deteriorating, and so on. Specifically, when you have multiple environment. So training a reinforcement learning agent becomes difficult at number of times. So that's why keeping it extremely simple, A3C model seems to be doing good, and so on. So I'll just skip this part because I'm not sure if you enjoy this. Those of you who are looking for a holistic course, you can go for this upcoming PG certificate courses. And it's a pretty deep dive course, and it covers everything from scratch. It's an 8 months course. And there are 2 professors from IIT and industry leaders who will be teaching this course. All right. It covers almost everything in machine learning and deep learning. And you can just subscribe to CloudxLab and access all the premium content at just like 600 rupees per month. I hope this was a good motivation to all of you. Feel free to give me a feedback using the form, and reach out to us at CloudxLab if you have any doubt. Stay tuned. I'll be doing more webinars, and we'll be doing more deep dives. All right. With that, let me just switch to your questions. There are a couple of questions that people have asked. A question is replicated learning is same as behavioral cloning? Yes, it's actually I was using the term replicated behavior. It's essentially behavioral cloning. And I think The more common term for replicating behavior is behavioral cloning. Okay. In replicated environment, do we create parallel environment always? Good question. Question is, in the replicated environment, do we create parallel environment always? Not really. Almost every reinforcement learning, we always create parallel environment. Okay, almost in everything, whether we are doing genetic or whether doing other things. So we do utilize multiple machines at the same time to play. Okay, and we gather all the data and then do that, because almost every algorithm starting from the first algorithm called reinforce, right, from where the name reinforcement learning comes. Okay, reinforcement is a misnomer for many people, because reinforce looks like that we are making it overfit, right? We are making it memorize, and forcing it. No, reinforce is essentially, we got a reward after some time. We go back and reinforce that reward in the past actions. That's why we call it reinforce. Now, replicated in all the reinforcement learning, one of the common strategy is let your model play for some time. And it's better to do it parallelly. Almost in everything, we always let it gather data in parallel. Okay, because playing takes time, its own time. You can't really make it fast because every game has its own mechanics and dynamics and wait period and so on. So you can't really make it fast. So it's better to just do it parallel, because when you're playing, it's not really consuming too much CPU cycles, because it's not like training or GPUs. It's essentially the computing. Okay, so yes, in most of the reinforcement learning, we do create parallel environments. How reinforcement learning will react to unknown problems for which it has not trained, meaning can it learn in the same way as we humans learn by watching? Exactly, that's the whole point of machine learning. If a model is not able to predict in unseen circumstances, the circumstances it has not seen, it is not really learned. It is memorized. And when you are training a model, your strategy is to avoid memorization. If your model is not generalizing, right, that means you got to regularize the model, beat the model until it generalizes. Okay, it's a very common misconception that machine can only predict the things that it has seen. No, it predicts the things that it has not seen before. Like, for example, let me ask you a very simple question. That imagine, I'm going to just take extremely rudimentary example, right? You all have seen, let's say, this is, right? This was the one point, this was another point. Let's say this is years of experience, and this is the salary, right? And we have some data and we drew a straight line going through them, right? Now, it has, let's say, only seen probably these few examples, right? These few examples, okay? And we came up with this straight line that's fitting through it. Now, will it be able to predict things which it has not seen before? This age it has seen, this age it has seen, this age it has seen, this, I mean, not age, years of experience it has seen, right? But this year of experience it has not seen before. Can it answer this question? Yes, that's what is machine learning model for. Okay, so if your model, any machine that you're training, if it's not predicting for unseen circumstances, right? That means it's a disaster. It is just memorizing. Okay. So I hope I answered your question. Yes. So the idea is, how can we make the machine learn the way human learn, right? The challenge is that one of the biggest challenge in case of reinforcement learning or anything is that we don't know what's a reward. Okay. So most of the model, the way the training works is there is a label and there's a reward we design around the label. Okay. And then in real world, rewards are very, you know, sparse. They are rarely available. Okay. They are rare. I mean, how many times I got a reward, right? Like the only reward I know is of food. But most of the things I learned by without the food, without food being my reward. I learned around playing this, pushing that. I learned about, okay, what does it mean by the weight of this thing, and so on. So I learned all of that. You learned all of that without reward. So the biggest challenge with respect to the machine learning is how can we make the machine learn without explicit labeling, explicit rewards. Okay. And of course, right, there are many more things. Okay. Many more things there. To reach the human level, it's going to take time. There, it is we are going in the right direction. We've reached somewhere at least, but it's going to take some time. All right. Is reinforcement learning cost effective when applying to robotics? Okay, good question. So there are certain examples where reinforcement learning is hard. Okay, reinforcement learning is hard and difficult to apply. For example, many things can be simply coded by you and they will work well, like for example, balancing, right? But that code will only work in few circumstances. But if you train the machine or a robot to start learning by itself, learning to balance itself, learning to do things, that is way more better. And that's the only stable way of building robot. Okay. Because all the things that if you code and they'll only solve this small issue. But if you can design a robot which can essentially learn by itself, learn to figure out the goal and objectives and everything, it is going to be, I mean, that's going to be the real robot, because people have tried all kinds of robots. They become, they're not as intelligent as a pet dog or a pet cat. Okay. Therefore, if you really want to build a robot, they have to be based on machine learning and not rule-based. Okay. And same is true with everything. All right. So I hope I was able to answer your questions. I'm sure that you will, I'm sure you will get certificate. There's somebody who is too worried about certificate. Okay. I think my request to everybody is no matter what you're doing, pay attention to learning things. Certificate will only take you there, but it won't make you successful. This is, this particular topic is something that, something that people have been trying to do for thousands of years, right? You see, Mary Shelley wrote Frankenstein, right? That was a fantasy. So here we're trying to figure out how do people think, and yeah. So my request to all of this is that if this topic doesn't give you an interest, what will? I think this is like most important topic that you should pay attention to. And this, like, if you pick psychology, if you pick any branches of science, it's all about, figuring out how things work, how do people think, how can people think better, and so on. Okay. And this is where we are. So rather than worrying about certificate, or rather than worrying about anything else, focus a lot on understanding this topic. This topic is a breakthrough. This topic is going to has already impacted the whole world. I mean, thanks to ChatGPT last month, it's just a breakthrough. A question is, how much memory does a machine need when it tries to use reinforcement learning for learning a thing? Good question. It all depends on what are you trying to learn. The example that I took, poll cart, it doesn't take much memory. You can just train it like half an hour, as well as it just runs in like maybe say few megabyte of memory. Okay. But the memory is a function of how deep neural network you are trying to build. And why do you need to build deep neural network? When you have a complex problem, large complex problem, having so many moving parts, and you have so much of data to train it, in those cases, you need bigger models, bigger memory, and so on. All right. Thank you so much. I enjoyed your questions. If you have any question, any more question, come over to the discussion forum, and I would love to answer your questions. And this is a topic that's close to the heart for the whole world as of today. And yeah, machine learning is something that probably everybody, every kid I met at every top college, everybody is just focused on it. And that's the right thing because there are so many dimensions to it. Wonderful. Thank you so much. And you can reach out to me on LinkedIn as well. You can find me on LinkedIn, reach out to me. And if you want to have a discussion, drop me a mail or just leave a message on the discussion forum. Thank you so much. And I love to get feedback. So fill the form and see you at CloudxLab.